We have four talks. We're starting with Willem Hare from Strathclyde, and this talk is on thermal effects in liquid crystals.
Okay, hi, so I'm William, and my talk is called Thermal Effects in Liquid Crystals, but really it's just going to be about everything I've done so far during my PhD, so a lot of it is just going to be about Newtonian fluids. So I'm going to start off a bit by talking about thermally driven convection within Newtonian fluids, such as Rayleigh-Benard convection, and then a bit about the Marangoni effect. After that, I'm briefly going to talk about Ericsson-Leslie theory, and then I'm going to talk about how this applies to convection within liquid crystals. And then I'm just going to say a bit about what I plan on doing in the future. Okay, so Rayleigh-Benard convection, it's a fairly simple setup. You'll have a liquid, and it's going to be want to heat up from below. The liquid could be between two parallel plates, or you could have an upper free surface. I've shown that diagram here. Now, when the temperature difference across the liquid becomes great, the buoyancy effects are going to cause an overturning instability to occur. And then the governing equations for this system are obviously the Navier-Stokes equations and the heat transfer equation. And then we can write down the linearized form of the equations here, where R is the Rayleigh number and PR is the Prandtl number. And then from equation 1 and equation 2, we can combine them to get this equation 4 out here, and it can be equations 3 and 4 we're going to try and solve to find out the onset of instability for this system. We have our boundary conditions fairly simple. At a rigid boundary, we have no penetration, and the second condition comes from no slip and also the continuity equation. And the temperature is zero. The temperature fluctuates to zero because we assume the temperature was constant on the boundary. For the free boundary, again, it's the first one comes from the kinematic condition, and the second one is from the tangential stress balance. And then we're going to take normal modes of this form here. We can substitute them back into our governing equations, and then we can solve this at marginal stability, which means that the S term equals 0 to find the dispersion relation, and then we can plot. Then we'll find that this is of that form here. And we can then plot this dispersion relation against the wave number to find this critical Rayleigh number, and the system will be stable for any Rayleigh number smaller than that. Okay, then we're going to talk quickly about the Marangoni effect, which is a fairly similar problem, except this time we have to have a free surface, because now the instability will be driven by the variation of... sorry. Oh, is it? I think it's on, but... sorry. I'll try and speak louder. Okay, so now we're going to talk about the Marangoni effect, which is fairly similar to Rayleigh-Benard convection, except this time it's driven by the variation of surface tension with temperature. So we have to have an upper free surface. And obviously, areas with fluid is going to try and flow from areas of high surface tension to areas with low surface tension, which is why the instability is going to occur. And again, the governing equations are fairly same, except this time we have neglected buoyancy, so our Rayleigh number will be 0. The main difference here is the tangential stress balance, and this will give us a very different boundary condition. Because surface tension varies with temperature, we can use the tangential stress to find these relationships for the Marangoni number, which is what we're going to try and solve for. We can then apply the continuity equation to get this equation here. Our other boundary conditions are very similar, except this time we assume the free surface is a perfect insulator, so instead of having the temperature constant, we just say that no temperature can flow through the boundary. Again, the next thing is fairly similar. We do a linear stability analysis, so we take normal modes and then substitute that back into our governing equations. And then again, if we solve at marginal stability, we'll find the critical Marangoni number, which we can then plot against the wave number, and we'll get very similar again. Anything? Oh, okay, we seem to be having some technical difficulties. I'm going to wait and see if it comes back. Yes. Yeah. Yeah, only linear stability analysis. That's all I've done so far. What? Sorry. Yeah. This is just basically the work I've done in the first few months of a PhD. All this has been done before, essentially. We're going to try and eventually apply this to liquid crystals, and then really in the long term, we're going to try and do this with pneumatic droplets. That's a sort of long-term goal, but everything I'm talking about today has been done before many times. There's no new work here. Okay, well, so basically, instead of Rayleigh-Benard convection, are you familiar with that? Now, instead of instability being driven by buoyancy, we've neglected buoyancy. It's driven by a difference in surface tension. So you have a surface tension that will vary with temperature. So obviously, if you get fluctuations of temperature, you get fluctuations within the surface tension. So then fluid's going to want to go for as low surface tension rather than for as high surface tension, and that's what's going to drive the instability. Yeah, that's true. Yeah, yes, you will include. Yeah, yes, it's just giving a very simple example of basically what these things are. You're right. In practice, you will have both effects occurring at the same time, but it's just meant to be a brief introduction, and then we'll talk later about how we can use both. We'll basically, in reality, use both, but we haven't done that yet. That will be something we'll look at later. Well, experimentally, essentially, it's just you heat it up, and once the temperature difference becomes big enough, you'll get an instability. That's basically it. And what you'll get, like what often are called rolls. It's quite hard to explain. And I should probably have included an image of what it would look like. It's hard to describe it while speaking, but I'm not an experimentalist. I just know a wee bit. Yeah.
It's quite similar, near the threshold. Above it.
Okay, so I'm going to get started again. So I think we're just talking about the Marangoni effect. Okay, so let's just go back through that again, or have you all understood most of that? Okay, so let's start here. Okay. Well, so the Marangoni effect, again, we have a fluid with a rigid lower boundary and an upper free surface. And then we're going to heat the fluid from below, and that's going to cause an instability to occur due to the variation of surface tension with temperature. And again, we've got our governing equations of Navier-Stokes and the heat transfer equation. Then we do our tangential stress balance, which will give us a condition for the Marangoni number, which is what we're wanting to solve for. And then we obviously have our other boundary conditions, which are given by the kinematic condition, and also the temperature we've assumed cannot flow across the boundary. And the other conditions of a rigid boundary will just be the same as before from the previous case. And so we'll take normal modes, we'll do our linear stability analysis, nothing difficult there really. And then we find this relationship for Marangoni number against the wave number Q, which we can then plot here, and anything under that curve will be stable, and when it's above that minimum point of that curve, it'll be unstable. So the critical Marangoni number we worked out to be about 79. And then also the aim of this is to apply similar techniques to liquid crystals. So I looked quickly at Ericsson-Leslie theory, and most of you will be familiar with that. But because we're considering thermal effects, we'll also need to include this heat transfer equation, so we can consider convection within liquid crystals. And then I looked at a paper by Dubois-Violet where we consider two specific cases. We have a case where we have a homeotropic case where all the molecules align parallel to the two plates. And then what we're going to do is we're going to heat the sample from above this time. And then in the basic case, it's fairly simple. The heat will just travel straight through perpendicular to plates. But if we allow the direction of the molecules to fluctuate slightly, heat will now travel along the direction of the molecule like this, which means we'll get an uneven heat distribution with some areas being extra hot and some areas not being. And this will cause an instability because this really hot area here will try and move up the way, and then it'll have to be replaced by fluid coming in here. So this is what's going to drive our instability in this case. And very similar, the planar case, basically the same thing, except this time the molecules are aligned parallel to the plates. This time we heat from below. Again, you'll get an uneven temperature distribution. And then again, that's going to cause our instabilities here. So we wanted to do a wee bit of analysis of this, so we basically did the same thing. We did a linear stability analysis. So we took normal modes of this form here, where Qx is the wave number in the horizontal direction, and Qz is the wave number in the vertical direction. And then basically we substitute these into our linearized Ericsson-Leslie equations, and we'll get all these relationships out for the homeotropic case. This one comes obviously from linear momentum balance in the z direction, this from linear momentum balance in the x direction. This comes from the heat transfer equation, and this will come from the angular momentum balance. For the planar case, it's a very similar set of equations, although as you might notice, some of the terms are slightly different. Like this one's an alpha 2, whereas here it was alpha 3, so it's very similar but just slightly different. And then what we do from these equations, we can get this relationship here, which will give us the horizontal wave number in terms of a vertical wave number, which will then allow us to eliminate one of these terms from our system, which then hopefully we'll be able to solve, which now we'll be able to solve subject to these boundary conditions here, where essentially we have the no penetration condition, the no slip condition, constant temperature in the boundaries, and this says also that we have strong anchoring, so the director fluctuation will be zero in the boundaries as well. And then we can solve. So then now we can be able to solve this system to find the onset of instability, but you can't do this analytically. It would have to be done numerically, which unfortunately I haven't done yet. But from paper, you can see it looks something like this. We've plotted the difference in temperature between the plates against the wave number in the horizontal direction, and we found the critical temperature difference for a homeotropic case is about 40 degrees, and for a planar it's about 21. That's basically all I've done so far, but what we're hoping to do is to look at maybe similar problems but with an upper free surface, and then we'll have to include the Marangoni effect when we do that, because obviously both will happen simultaneously. We'd also like to look at weak anchoring instead of strong anchoring, as obviously that will make a very big difference. And really the long-term goal is to try and apply this to pneumatic droplets. That will be the actual new work that I will be doing, and that should hopefully happen in the near future. So that's all I've got to say. Thank you very much.
We have quite some time for questions, even though there were all these problems with the start. But any questions?
Yeah.
Okay.
So could you go back to the picture of when you had the instability in the liquid crystal?
Which one?
So yeah, this one.
Okay.
I don't really understand this. So is there some analogy in the sort of thermal conductivity of the fluid along the director? Or, I mean, I don't.
Well, essentially, what happens is the heat will travel along the direction of the molecule. So if the molecules are tilted slightly, the heat's not going to move straight up as you would have in a Newtonian fluid. So you're going to get pockets of hotter areas. So you get some bits are going to be hotter and some bits going to be colder.
Right.
And then the hotter areas, their density will decrease. So they're going to want to move up the weight, and the cold areas are going to want to move down the weight.
No, I understand the sort of mechanism for the rolls, but I don't really see why there's some anisotropy in how the heat flows. I don't really understand that, but if it's true, then
it's just one of these things.
Okay.
Heat travels along, and the liquid crystal will be the heat will transfer like perpendicular to the molecule and parallel to the molecule at a different rate. So it's angle that sort of travels along the axis of the molecule.
Okay.
It's just one of these things you kind of have to remember.
Also, I'm not really too familiar with the Ericsson-Leslie equation, so can you just remind me what the alphas and the etas were?
The alphas and the etas of that was...
So there's some parameters in your, once you linearise, I think. They're probably just viscosities or something.
Here, the alphas and etas.
Yeah.
Essentially they're just combinations of the Leslie viscosities. It's just like a combination of alpha 1, alpha 2, etc.
There was one.
So you had the sketch that you just showed and the one on the slide before.
Yeah.
And in one of them you put the temperature at the top, the higher temperature, and the other one on the bottom. Does this matter in this case, or shouldn't it?
Yes, it does. Essentially, well, I think the reason for that is if you look at the sort of direction of the instability here, it's going to try and turn the molecule sort of further away from its original orientation, which is perpendicular to the plates. Whereas if we heated from below, it will be in the other direction, which would try and turn it back towards the original orientation. So it would have a so the flow would have a stabilising effect. So I think the instability would sort of die out, or maybe not even occur. It's hard to explain, but I think that's the reason for it.
But in the other case, you had parallel anchoring at both sides, right?
What? Sorry?
In the other sketch?
The others? This one?
What is the anchoring here? It's planar on
it's planar anchoring, yeah.
On both sides?
Yeah.
Well, maybe I have one question. Do you have experiments with the liquid crystals that? Are you assuming here that the convection is?
Yeah, the experiments have been done, and they just saw convection occurs in rolls, as we were mentioned earlier.
And from those experiments, do you actually get this correlation with the alignment, or with the?
Yes, it's been done experimentally.
Mm-hmm. Any other questions? Well, we're on time, I think. We still have a couple of minutes, but we can maybe start